Welcome. I thought you may miss traveling in the times of Corona, so I would like to take you to a little trip in space and time. We actually start going back 4,000 years to the Middle Ages. This was the time when the first experiments were performed, establishing what we call the first paradigm of material science. It was much later, just 400 years ago, when the first theories came into play with the laws of classical mechanics, with electrodynamics. Since then, many different theories and concepts have been established, including quantum mechanics, which is the basis for our daily research nowadays. Only 40 or perhaps 60 years ago, there was a third paradigm came into play. It started with density functional theory and other theories like molecular dynamics, Monte Carlo simulations. And these theories, together with the ever-growing computer capacity, allows us nowadays to perform computer experiments and also high-throughput computational screening that's getting more and more popular nowadays. All these three paradigms together, they form, again, the basis for what we're doing in our daily research. So let's have a closer look into this. What is physics today? And in order to discuss this with you, I would like to introduce my group to you, or at least part of my group. So you see the group is big. My background is solid state theory, but also I'm dealing also with many aspects of computational material science. And that's why some of my group members, they are working with pen and paper. They are implementing computational concepts. Others are running calculations for exploring materials and their properties and functions, and many of them even use very large high-performance computer capacity for this. Now, what's the outcome? Of course, the outcome are papers. We're publishing nice papers. This one, for instance, it's dealing with a light-emitting nano-object, or at the right side hand here, we see a hybrid inorganic-organic material that may be useful for optoelectronics. Or in the third paper that I have collected, this is all about a class rate material that may be useful as in a thermoelectric device. So let's just take this and have a closer look into this. What do we find inside? So I'm not going to talk about the physics. This is not a physics talk, so I don't have time for it. Nevertheless, I would like to take 1 minute to explain you what is the concept of this paper. So it's all about class rate materials. These are these beautiful cages, for instance, made out of silicon. These materials are semiconducting, and this is a good property for a thermoelectric device. So what we don't like in thermoelectrics is a good thermal conductivity of this material, and in order to reach this here, our chemist friends, they put either barium or strontium, so something heavy into these cages, to prevent the thermal flow. So what do these elements do in here? Barium and strontium are ionic. So they are doping the cage, they make the cage metallic, and in order to get back to the semiconducting state, we need to replace some of the silicon atoms now by aluminum. Right? And indeed, if you look at this x-axis here, which gives you the aluminum concentration, you will see that the lowest energy configuration, this is the green dot here, is indeed a semiconductor, which you recognize very easily by looking at the density of states, which is 0 around the Fermi level. However, if you go to somewhat larger energies, there are also many different configurations. Some of them are metallic, and this is indicated by this yellow dot, for instance. If you look here at the density of states, then you see that it's finite at the Fermi level. So what the outcome of this paper is basically that we emphasize that this material may be good, but may also not be too good for thermoelectrics, because at higher temperatures it could exhibit metallic character. So nevertheless, let's have a closer look into this paper, and I would like to use this to exemplify how we publish. Right? So what do we typically find in the publication? It might be a table. Yes, we have it in this material. Don't try to read it. We have a figure, of course, we have even several figures in these papers. Well, we have a structure, yes, this is what we have seen already, these are the class rate structure. Maybe there's a few other numbers that we extract from all the knowledge that we have gained on the way of working on this material for 1 or even 2 or 3 years, or even longer. So in essence, what we publish is never the full information, right? So don't take me wrong, I really love to work with my students and postdocs looking into a very dedicated problem of a specific material, but overall, given the challenges that we are facing by finding better and better materials, by finding even novel materials in order to solve the problems we are facing in terms of energy or environment, this is a very, very slow process. So our research is great, but maybe it doesn't lead us fast enough to the goals that we want to achieve. So let us dream. Imagine someone gives you all data from theory and brings it together. What does it mean? That we can somehow explore and exploit the full wealth of all calculations that have been performed on this planet for many, many years, and this will be so also in the future. Before I continue exploring this dream, I'd like to introduce the data to you, right? So, and I use actually, again, the thermoelectric figure of merit as an example for doing so. The thermoelectric figure of merit is basically one number that tells you whether a material is good for being exploited in a device or not. What do we need for computing it? Well, first of all, I have to emphasize that we need to do all the calculations for a large temperature range because we want to recover waste heat, which means that we want to use the heat that is appearing in any device or in every machine in order to transform it into electricity. So we want to know the properties of the material for different temperatures. The properties are the geometry that we want to know. These are the phonon spectra because they give us the thermal conductivity, but we also want to know the electrical conductivity in order to finally get the thermoelectric figure of merit, which is the ratio between these two. Now, in order to do so, we have to employ different levels of methodology, and this starts with density functional theory for the ground state. It will be many-body perturbation theory for the excitations, maybe density functional perturbation theory, or even ab initio molecular dynamics in order to get the vibrations and the thermal conductivity. Now, if we look at the right side here, then you will see that it's not just a few kilobytes or megabytes that we produce by computing just the properties of one single material for one temperature, but we may create, depending on the complexity of the material, gigabytes or even several terabytes on the way. So it's quite clear that the few numbers that we publish will never contain all the information that is inherent in all this data that we have created on the way. So this was the reason actually why we started to collect our data, and not only started to collect them, but we also put this data collection open. So this is what the Nomad repository is. It's a collection of computed material science data. Is a part, actually, the entrance level of what we call the Novel Materials Discovery Laboratory. And I would like to give you a little guided tour through this laboratory. But let me just emphasize one point before. First of all people doing electronic structure calculations on these planets, they are invited to upload their data to a central repository. This is the Nomad database here. And so far, obviously, it has been very successful because so far we have collected already more than 100 million calculations. So this is since 2014 when we opened up this repository. And well, this actually brings us already to the fair, or the aspect of fair data, because a repository makes data findable, right? But I also want to point out that in 2014, when we established this repository, the expression fair in terms of data handling was not even written down. So the famous paper about fair data handling only appeared in 2016. So we have anticipated fair data already at that time. So if you're interested in the data infrastructure, I'd like to point you to Markus' poster. He will be very happy to discuss with you because he is our architect on the data infrastructure of the whole NOMAD laboratory. So Markus is also responsible for, so to say, bringing all this data to the cloud. Actually, data are not sitting in the cloud. They are hosted at the Max Planck Computing Center in Garching. But anyway, they are sitting now all in the NOMAD database. And well, since people upload data, this makes data findable, but of course it also makes it accessible because you can download the data again. So let's have a closer look into this database, right? So if you look into this, what you find there are folders and files where all the input and output files of this 100 million calculations are sitting. And this is actually great, not only because we are very organized nowadays, but it's also great because those people who are expert in such calculations, they can use them. So they can look whether they get the same result as other people do. They can use, don't know, input files or crystal structures that had been donated by others. And they can do much, much more with this data, right? But if you ask the question whether this data is really accessible to those people who, for instance, want to create a new device, or experimentalists who want to know what the outcome of such calculations is, we have to do better. And in order to do so, we have established what we call the NOMAD Encyclopedia. So the NOMAD Encyclopedia is basically a search machine that makes data human accessible. So you can search for a material, for instance, by composition or by let's say material's name, or even by properties that you're interested in. The encyclopedia will give you a list of this, and then if you choose the material of interest, it will show you all the information about the structure. It will show you if someone has computed a band structure, density of states, could also be phonon spectra, thermal properties. So whatever people have computed on this planet, you will find this in the encyclopedia in a human readable and also visualized, nice visualized form. So also for this we have a poster, so Martin and Shimon will be very happy to show you how they use the encyclopedia, and I hope they can also convince you that the encyclopedia is not only a service to the community and a nice picture book, but you can also use it for research. Because, for instance, only comparing calculations from different methodologies, different codes, different levels of accuracy, you will see what the impact of all these parameters is to the results. Let me move on in the fairness of data, and I come to the I here. I is interoperability, right? So if you think about that, people from all over the world have contributed the data to the NOMAD repository. So all these 100 million calculations, they have not been created by one person, neither by one computer code. But you see here from this graph that the whole community uses quite a lot of these tools. So far, we support at least 40 different computer codes. And I emphasize here that, well, we have to parse all the input and output files because we want to extract the information that's inside there, right? Otherwise, you cannot compare different codes, and there is no way of being otherwise interoperable. So what is the most crucial point for getting there? So writing parsers, of course, is one thing, but in order to be able to write a parser, of course, you have to describe the data first. And this brings me to the very, very important aspect of metadata. So I couldn't make enough exclamation marks I would like to put here. That means we need to describe every single quantity that you find in an input and output file. Only then you know why, for instance, the total energy 0 in the WASP calculation is different than in an ab init calculation or in any other code. We need to know this. So in other words, we need a very unique description of all this data. And I'm not going to talk more about this metadata standard, but I want to point to the talk by Luca Ghiringhelli. He will address this issue in very detail. So, bottom line, what we find in the NOMAD archive nowadays is normalized data, so the same data as in the repository, but they're normalized in the sense that they're now exhibited with the same file formats, the same units, so in a unified format. Well, needless to say, this is just the first step in terms of interoperability. Actually, I'll get back to this because I consider interoperability really to be the biggest challenge and the biggest hurdle when bringing data from different sources together. Why is this so? Well, I'll discuss with you later on. I'll get back to this. Let me now get back to my dreams, right? So we imagined that someone brings all the data from theory, but in essence, theory is just one paradigm, one pillar of materials research, and of course, very important are experimental data, and equally important, all the information about how these samples and the material have been synthesized. So let's imagine we have all this together. Then we can start dreaming further. And I like to share with you my scientific vision of where we like to go. So let's assume, well, or just imagine, consider we have a map of Europe, and on this map you will easily distinguish where you find people that speak German or others speaking English or speaking Dutch or whatever. We would like to create similar things to distinguish between materials that are useful for, don't know, superconductivity, for transparent metals, for solar absorbers, thermoelectrics, thermal barriers, dielectrics, you name it. So we would like to find in all this space of materials in terms of composition and configuration where in this space we can find these materials. So in other words, it should look like this. Basically, we should get a map where we can tell you, well, if you go to this region, you find, for instance, very good superconductors. So in order to do so, of course, we have to do more, because we have to find out what is behind this function, right? So if we want to explore the trends and patterns, we have to find out what these descriptors are. So descriptors are the parameters that somehow are the actuators behind a certain function of a material. So I'll get back to this, but let me first ask the question. We have now all data from synthesize, from experiment, and from theory. Is this enough to fulfill our goals? Well, unfortunately, the answer is definitely no. And I'd like to share with you why I think this is so. And this, in fact, brings me back to not only the first transparency, so our travel in time. Now, actually, we would like to go in future, right? We want to like to go along this axis. But at the same time, we would like to address the issue of the R in FAIR. R means reusable or repurposable. What do we mean this is? We mean if we bring together all the data from the community, of course, we can use the data for something different, very different to its original purpose, repurposable, right? So, and this actually establishes the fourth paradigm of materials science, which is big data driven science. So our future research will be about finding such patterns, finding such trends, even finding anomalies. I'm coming back to this, by exploiting big data. And the crucial point here is, why did I say no before? Because we have to have the tools before. So we not only need laws, like in classical mechanics, we not only need the computational tools, we need novel tools in order to go there. And these novel tools should be tools of artificial intelligence. So, well, this is very general, of course. It not only refers to material science. So if you look into this paper that was not published by Jim Gray, but Jim Gray was the person who established this fourth paradigm, if you like. This was a very general comment and a very general statement. And in fact, there are many, many different communities nowadays who really use machine learning and artificial intelligence to explore new grounds. Which are these communities? There are many areas. Well, you name it. For instance, in linguistics, in bioinformatics, in computer science, many, many different tools are established here, right? Not to forget also, for instance, social media, which maybe are the biggest driving force behind machine learning nowadays. So, couldn't it be that we just use all these tools that all these communities are establishing or are developing just for our own purposes? Yes and no. So we definitely can make use of this, but we never can take it from the shelf. I think material science is much more complex than, for instance, problems in social media, where it's good enough to distinguish between colors that people like when they buy clothes or the shoe numbers in buying shoes. So material science is much more complicated, and that's why I think we really need to develop novel tools that are informed by physics. So in other words, the domain-specific knowledge is really important. Of course, I mean, look at neural networks are very important right now. We use it also in our area. There is subgroup discovery, there is compressed sensing. There are many, many different things like trees and forests. All of this is very nice, and we also use it, but it cannot uniquely lead us to the goals that we want to achieve. So before I start sharing with you my vision of what our future research will be, I'd like to just point to two talks, one by Mario Spolai about subgroup discovery, the other by about compressed sensing by Runai Ouyang. So what is my picture of our future research? Well, of course, I've shown you before, we would like to explore these clouds, we would like to learn about trends and patterns of materials research. And I would like to emphasize 2 points here that I somehow already have indicated. One is that we need novel tools that are informed by the knowledge of our community. And very important in this context is that these tools go beyond interpolation. So what we need is models and methodology that really has enough predictive power to take us out of the box. What do I mean with this? If we only consider materials for, dielectrics, which we know are good for dielectrics, we will never find something crucially new or very, very new. We always find probably something which gives us incremental progress, but never something completely novel. So if we have explored, let's say, materials for thermoelectrics or thermal barrier coatings, we would like to use the same data for exploring something completely different. And in order to do so, we need predictive power, right? The other point I would like to make is that we also need the right data, because what we want to find finally is a pearl, right? We want to find something exceptional, and we want to find outliers. I don't talk about the outliers that are bad data. I would like to point to outliers that are really something spectacular. So in other words, if we increase the amount of data and we increase the amount of data that gives us more information about the sand on the ground of the sea or the water molecules, this wouldn't help us. We need the right data in order to increase the information about these pearls. So I don't have time to talk about different, let's say, concepts that we have explored already, but I would like to point to you the analytics toolkit, the Nomad analytics toolkit, which gives you already an idea about the first steps that we have taken into this direction to create maps. Just in a first glance here, this is a few examples. On the upper left, you see, for instance, some tool for crystal structure prediction, a very famous old example, by the way. So if you give me two atoms, A and B, I can tell you what the crystal structure of this material is. So would this be synthesized either in rock salt or, for instance, in zinc blende? There are other classification problems for property classification, for instance. You give me a material, I may tell you without knowing it, whether it's a metal or an insulator, or it may distinguish between trivial and topological insulators, and many examples more. Just explore the analytics toolkit, or you may also visit Luca's poster, who will be happy to talk about it. So, where are we? In order to discuss this, I would like to introduce our host to you. Our host is FAIR-DI, and FAIR-DI is an association that stands for Fair Data Infrastructure for Physics, Chemistry, Material Science, and Astronomy. Well, you may ask the question now, what has astronomy to do with chemistry? So they may not share any scientific question, but when it comes to data infrastructure or fairness of data or processing of data or data, let's say, security or so, then it's, I think, a very good idea to also team up with other areas. Nevertheless, this conference is not about astronomy, it's really about this line here, about the material science component of FAIR-DI. However, compared to what I have been telling you so far, we not only consider theoretical data here, but we also include experiments, we include aspects of synthesis, and also aspects of functional materials, different areas of functional materials. So, and this brings me back to the question I have been asking before, what about the complexity of the eye in FAIR interoperability? So what impacts the eye? There are many different things. First of all, variety and veracity. What does this mean in our research? Think about how many different experimental characterization techniques we have that gives you insight into materials, right? And that means that each of these techniques even comes with different variants, or there are many different vendors for these machines. Different machines have different resolution, different accuracy, different precision. So, and this is what we call veracity. So there is some uncertainty about the quality of the data or the correctness of the data. So this brings me to the topic of data quality. Well, in order to evaluate the quality, we need to set up something like trust levels. In order to do so, we need then benchmark data for everything. And also we shouldn't forget that there may be many hidden parameters that determine finally why the data are looking like they're looking. So all of this somehow has to do or impacts reproducibility of results, and that's why they're important for the eye if you want to bring different data from sources, different sources together. And well, there's also a poster only concerning theory. Daniel and Christian will be happy to discuss with you about trust levels of theoretical data. So, and this brings me to experiment. Just in a nutshell, and I emphasized this already when talking about the theoretical data, metadata are crucially important. So that means that material science data are only meaningful if you have an in-depth description of this data and how these data have been obtained. And this starts actually with the synthesis of every sample, how you treat the sample, also to capture the parameters of the instrument and to follow the whole measurement process, and so on and so forth. I just give you one very simple example that doesn't cover the full complexity, but at least gives you already some idea what I'm talking about. So what you see here is the optical spectra of different samples, different publications, and these samples are all called silver. Now, you may assume that silver is a noble metal, and you wouldn't expect that different measurements and different papers would give such a diverse, heterogeneous picture of this optical spectra of one and the same material, right? So this is definitely an aspect of veracity, uncertainty, right? But there are also different ways how you obtain one and the same property. In this case here, it's the dielectric function. So more or less directly, you can use ellipsometry for getting this quantity, but you can also measure absorbance or reflectance, but you also can use electron spectroscopy in order to get the same quantity. All of them, of course, none of these methods is really direct, so there's always evaluation processes for the processing of data until you get to the final results. And this, of course, brings in variety and at the same time also veracity. And yeah, needless to say that there's, of course, also many theoretical tools to compute the same quantities. So let me get back to these transparencies here and just give you an overview, don't go into details here, what the metadata are that we have to capture in order to describe, let's say, a measurement until the data publication. So it has to do with the sample, all data of the instrument, all data of further processing this measured data, finally all data related to the publication. So, and this brings me to the summary of this presentation that I would like to read to you, right? So, if and only if we build a comprehensive, fair data infrastructure that captures all the aspects of data from synthesis to experiment and theory, and interweaving data, metadata, and processing tools with novel concepts of artificial intelligence, then material science will reach a new level. So let me ask a question again where we are. Actually, we have an idea where to go. We have seen already all concepts that we have established for theory. But, well, I'd like to introduce Fermat to you. Fermat is basically an offspring of FAIR-DI. It's the material science component of this association, which not only has an umbrella for theory, we also have an umbrella for synthesis. We have an umbrella for all kinds of experimental techniques. And very important, we also have an umbrella for use cases. Because finally, at the end of the day, whatever we do in order to process data from synthesis, theory, and experiment, it's the people who work on specific functions and materials and different areas of research that will tell us whether all of this is meaningful to them. Yeah, with this, I would like to stop. I hope that I have shown you that we have taken off on the way of reaching our goals. Of course, you see below here that is still very well-known land that we have here. So in other words, we need to fly much higher. But I think, as I said, we have taken off. And I would like to thank you for your attention.